What's up, everybody? Alright, continuing section 4.3 about exponential functions. And what we're working with now, and our second goal for this section, is how you can graph transformations of exponential functions. Okay, so in the previous video you learned how to make a table of values, essentially, in order to graph an exponential growth function or an exponential decay function, and you know what the general shape looks like and where the asymptotes are and so forth. Now we're going to try to graph transformations of either an exponential growth or decay function. Well, here's the first example. Lots of directions here. Given the graph of f of x, what I'm going to want you to do is sketch the graph of g of x on the same set of axes. Alright, now I'm giving you a function here, f of x equals 2 to the x power, and we're going to have a transformation of that, and then we're going to be able to sketch the graph of the transformation given the graph of the original function. This is a lot to copy down, so I would suggest that you copy down the directions here in the graph that I've given you so far, then focus on how you actually do the transformation. Go ahead, take some time to do that. Alright, so what I'm wanting you to remember here are some things we learned back in chapter 1. How do you translate? How do you reflect? How do you dilate a function? Alright? Now, you can see the difference between function f of x and the equation for function g of x, right? We're adding 2 to the input value of f of x in order to make g of x. And whenever you add 2 to the input value, remember that indicates that you're going to shift the graph 2 units to the left. Okay, so all we really need to be able to do is take the exact same points that we already have and shift everything 2 units to the left. So we're going to find some corresponding points. Now the one point you know for sure exists on this graph is 0, 1, correct? Because that's on the graph of every basic exponential growth or decay function until you start translating and dilating and so forth. So what we're going to do first is we're going to take that point 0, 1 and we're going to translate it 2 units to the left. So negative 2, 1 is going to be there. And then if you have some other points, you can shift those 2 to the left. We've got a point 1, 2 here. Alright, we had the point negative 1, comma 1/2, so that could be translated this way. And really 3 points is enough once you know the shape of these exponential graphs. So there's the graph of the translated function g of x. Fairly simple, right? Now another thing that you ought to be able to do is you ought to be able to identify what the intercepts are, if you have any, and you're always going to have a y-intercept. And so let's figure out what the coordinates of this point are right there. Not what it looks like, but what it actually is. And the simple way of doing that is to plug 0 in for x. If I plug in 0 for x, I'm going to get 2 to the second power, and 2 to the second power is 4. So that intercept then is the point 0, 4. So not quite what it looked like just when I wrote the shape in. That's why we're actually plugging in 0 into the x coordinate in order to figure that out. Pretty simple, right? Alright, let's try another. Okay, you see this function f of x equals e to the x, the natural growth function right there. And what we're going to do is we're going to graph g of x, which is equal to the opposite of v of x. Now, what's happening here is that we're multiplying the output value of e to the x by negative 1. And when you multiply the output value of a function by a negative sign, remember that's a reflection, and that's a reflection in the x-axis. So all we've got to do to make this graph here is reflect each of these points into the x-axis. Let's go ahead and try it. Alright, so that point 0, 1 is going to get reflected to 0, negative 1. This point 1, 3 is going to get reflected to 1, negative 3, and so forth. Alright, that's enough for us to be able to sketch our graph. And again, you always need to label that x-intercept, or y-intercept, excuse me, and so that's going to be 0, negative 1 in this case. Questions so far? Alright, not that I can answer them in the video, but make sure you save those for class. Let's go ahead and look at a couple more transformations that you can make here. Alright, now before we do this transformation, alright, where you see the input value has been multiplied by -1, I need to talk about something in comparison to what we did in the previous video. Because in the previous video, we said every time you got this negative x that you're going to have an exponential decay function. But if you pay attention to this graph for f of x, even though it's just a 1/3 of the positive x power, isn't that an exponential decay function? Alright, so another way to recognize exponential decay as opposed to exponential growth is to look at the base of your exponential function. And you want to see if it's greater than 1 or if it's between 0 and 1. We're never going to look at negative bases. Alright, and this is between 0 and 1. And since that is between 0 and 1, that means it's exponential decay. I'm going to write out that rule really quickly for you. There you go. I suggest you write that down. Anytime you have an exponential function in the form f of x equals a to the x power, if your base a is between 0 and 1, then that means you've got exponential decay. Alright, now that kind of gets reversed then when you put the negative sign. If you have an exponential decay and then you multiply the input by -1, then suddenly you're going to get an exponential growth function. Does that make sense? I'll try to illustrate why that would be exponential growth a little bit better here in a moment. But the focus for us right here is, can we make the transformation of this graph in order to get this graph over here? Now, multiplying the input value by -1 is a reflection in the y-axis, if you recall. So we just need to take each of these points and reflect them in the y-axis. And I'd normally say start with the y-intercept, except that if you reflect the y-intercept in the y-axis, it stays in place. Alright, so that point 0, 1 is still going to be the y-intercept for the new graph. And then let's see, -1, 4 is what that looks like. Oh, -1, 3, excuse me. So we'll reflect that to 1, 3. And how about we take this 1, 1/3 and reflect it to -1, 1/3. Alright, there's the graph of g of x. Pretty simple, right? And I'm going to label the y-intercept again, 0, 1. Okay, now I said I'd try to make it a little more clear why this was an exponential growth function over here, despite the fact that you got a negative x. Well, if we use our rules for negative exponents, when you have a negative exponent, you flip the base and change the exponent to positive. If you flip 1/3, you get 3 to the positive x power. Alright, great. Next example. Another one like what I was just talking about, where it's an exponential decay function at the beginning because your a there is between 0 and 1. Alright, now what we're doing this time is we're taking the output value of 1/2 to the x power and we're multiplying that by 2. A big thing that I want to point out to you with this is that you can't make this equation, and I hope you see why not. We can't say that 2 times 1/2 to the x power is just equal to 1 to the x power. Big thing that's wrong with that is we didn't follow order of operations. You have to raise 1/2 to this exponent before you're able to do any multiplication. Alright, so you can't multiply the 2 and the 1/2 until the 1/2's been raised to that power. So, not going to be the same thing as 1 to the x power. Alright, but it is going to be what I just described. We're taking the output values of the original function 1/2 to the x and we're doubling them. So, the point 0, 1, when we double that output value, it's going to go to 0, 2. Alright, the point -1, 2, double its output value, going to go to -1, 4. We have 1, 1/2 there. If we double 1/2, we're going to get 1, aren't we? Alright, so we've got enough to be able to make this curve. Alright, and that's how you graph transformations of exponential functions. Pretty simple, I hope. I will see you in class.